Michelle Gabriel Caldwell. Thanks for joining this module on controlled polymerization technology chemistries for wetting and dispersing additives. At BIC, we service many industries and end uses, and they all have one thing in common: incorporation of particles into a media. In some industries, it's easy. In others, it's quite difficult. And of course, we have additives for all of those challenges. These particles are mostly pigments and fillers, and they impart either functionality, aesthetic, or both. And they are all uniquely shaped and have different surface structures, treatments, and polarities. It's no wonder it's difficult to find the right additive for each application. Perhaps what's most telling is the strength of cohesive forces that keeps the particles in a low energy state of constant agglomeration. We review more of this in detail in the fundamentals module, but I bring it up here in the CPT module because reducing these forces is critical in high-end applications. To adapt to new technology, industry trends, and unique chemistries, as well as environmental needs, BIC's products had to evolve over time. And in that time, we end up creating different solutions to what is happening in the trends and the current issues in the industry. This adaptation takes place in our R&D facilities all over the world. As early as the 1960s, low molecular weight additives met the needs of the time. As reviewed in other modules, we take a stroll through memory lane to explain the impact and necessity of change. Today, we're going to focus on the advanced high molecular weight wetting and dispersing designs. The general design of wetting and dispersing additives can take on different forms. They can be copolymers, standard polymers, and have additional substances to enhance functionality. The archetypes are the main variables, with each creation providing unique properties for pigments and fillers, or making compatibility easily accessible for the resin groups, and improving, enhancing, and strengthening pigment affinity. Standard polymerization led to the first, second, and third generation of additives. And most polyacrylates in the earlier generations were designed by random polymerization, also known as free radical polymerization. CPT, or control polymerization technology, also has a few names, and it can also go by a subgroup called control radical polymerization. No matter the name, CPT acrylates will yield very structured polyacrylates. What are structured polyacrylates? They're used in this technology that can create a variety of polymerization techniques. We can look at things like ATRP, nitroside-mediated polymerization technology, or NMP, usually to produce alkyl oxide amines, or we can look at reversible additive fragmentation chain transfer, also known as living polymerization technology, or RAFT, in order to create the variety necessary. These polymerization technologies offer unique polymers with specific tailor-made outcomes. So the ability to place these different monomers exactly where we need them will yield either hybrids or end functionality, or environmentally friendly polymers, aqueous polymers, and so on. It is the placement of monomers during the polymerization that is desired. As standard, free radical polymerization yields polymers that are less than tailor-made, with no control over their placement. CPT opens up the polymer design, and structures can be created to meet industry challenges like water sensitivity, increasing stain resistance, reducing corrosion resistance, and actually even developing products that can work in a multitude of different systems. New wetting and dispersing additives with multiple and unique pigment affinity groups to improve pigment loading and viscosity reduction, also to increase storage stability, to improve color matching acceptance, to improve better compatibility in the resin system matrix, and also to enhance the application of resin-free systems, all by increasing the yield of polymer in addition to narrowing the molecular weight. A broader molecular weight definitely provides versatility. However, when we narrow that molecular weight, we're actually providing reproducibility. Many have asked, why do we need such sophistication for coatings additives? Well, when we're really focusing on the primary particle and the enhancement of deflocculation, getting to the right color, the right strength, increasing hiding power, as well as improving transparency, is a necessity to actually look at products that will be reproducible in nature and consistent with optimization, all without compromise. Of course, older generation additives can be used in certain systems if those basic needs are met. The evolution of products is a necessity, and we've made it easy to find these products by using the CPT logo. So when looking at what you can find beyond the standard industry additive like Dispersing 190, taking a look at Dispersing 2010, which could improve water resistance. Looking at Dispersing 2015, that can enhance the compatibility of pigment concentrates. Or Dispersing 2012, which not only works in resin-free systems, but also resin-containing systems. Dispersing 2013 has even more versatility and can be used in not only aqueous, but solvent and UV systems in very hard to disperse organics or carbon black pigments. Can certainly stabilize all of these systems with effective viscosity reduction, as well as improving all of the aesthetic properties. Explore the many other CPT acrylates in our product portfolio. Continue your journey with CPT additives by watching my video casts with the General Industrial and Use team. Thanks for your time, and should you need any samples or have any questions, please visit our help desk. I hope to see you soon in other training modules. Thank you. Goodbye.